Hello, Double E. This is a video on the basics of our turn signal timing circuit. We will have other videos about the more detailed internal operations of the 555 timer. So this video is just sort of an overview, and it's actually hopefully going to be helpful that we don't get too lost in the kind of nitty-gritty details. So let me just introduce you to my sketch here for a moment. Everything inside the orange line is within the 555 timer chip. In other words, you're not going to see anything that is inside this. You're just going to see like that little piece of silicon with its 8 legs, and that all of what I'm talking about inside this orange line is in there. Okay, everything that's outside this line, this orange line, is stuff that you hook up to the 555 chip. Okay, so you'll be choosing, for example, the values of R1, R2, C1, and then also VCC, and you'll be getting for your money the output here at pin 3. There's a couple of other things that you hook up, but we're not going to talk about those just yet. So there's a few things inside the 555 that I want to define. Okay, first of all is the symbol that looks like a triangle pointing to the right. That is called a comparator. And we're not going to talk about how the comparator does what it does in this video, but we will talk about that later. But it is important that we know what it does. The comparator does exactly that. It compares the voltages at this positive and negative terminals. If the voltage of the positive terminal to your capacitor is higher than the negative terminal, then the output of the comparator goes to what we call high. On the other hand, if the voltage at the negative terminal is higher than the positive terminal, then the output of the comparator goes low. What you'll see basically is that a comparator is usually hooked up to some reference voltage, which would be a constant voltage at one of the pins, and then the other input to the comparator is essentially going above or below that reference threshold voltage. Okay? So we have 2 comparators inside the 555. This top one is called comparator 1, and this bottom one is called comparator 2. Okay, the next thing that is inside the 555 is this, in this box here, this is called an RS or an SR flip-flop. Okay, the flip-flop is a digital logic circuit that we'll talk about the internals later. But really what we want to know about the flip-flop is what's going on at the output, which we call Q bar, okay? And that will be determined by what goes on at the inputs. The S and the R stand for set and reset, okay? We got comparators, we got the flip-flop, and then the last piece is this little guy here. This is called the inverter. Okay, when you see a symbol that just looks like an empty circle, that means not in digital logic, and this circuit essentially takes the input and it flips it upside down and sends it as output. So if the input is high, the output is low, and vice versa. So those are our 3 main devices on the internal to the 555 timer chip: the comparators, the flip-flop, and the output inverter. And then there's this other little thing at the bottom that I'll talk about later. So let's look at the circuit from left to right, and we're gonna sort of decipher what happens as the power is turned on. But before we do that, I just need to mention that the comparator values are tied to, for the comparator 1, the top comparator, tied to 2/3 VCC. VCC is just the positive voltage in your circuit. So we're going to assume that it's 6 volts for today. So 2/3 VCC is going to end up being 4 volts, but that is the threshold comparison voltage at comparator 1, and it's on the negative terminal. For bottom comparator, for comparator 2, the threshold voltage is 1/3 VCC, and it's at the positive terminal. Okay. Now let's look at what the comparators are comparing. Okay, comparator 1 and comparator 2 are both talking to, or I guess I should say electrically connected to, the top plate or the positive plate of the capacitor. So essentially the way that this circuit is acting is that the Comparators are evaluating the voltage at the capacitor plate, the positive capacitor plate, relative to 2/3 and 1/3 of the VCC, or the positive voltage, okay? Okay, so let's get to it. If you initially turn on the circuit, you've got 0 volts, okay, what we end up seeing, you connect the 6 volts, what we end up seeing is that the positive voltage starts to charge the capacitor through this pathway, okay? The charging path is through resistor 1, through resistor 2, and then ultimately C1 will start to charge. It's like a bucket filling up with water. So if we were to put a voltmeter across the capacitor, it would start at 0 volts, and then it would grow kind of like this kind of, this sort of shape. Now, when the capacitor's voltage exceeds 1/3 VCC, comparator 2 notices that. Comparator 2 says, all right, look, my negative input terminal just went from below to above 1/3 VCC. So this will set the flip-flop, which sets Q bar to low. The output inverter will then send a signal of high to the output. High in this case is going to be VCC minus about 1.5 volts. You don't need to worry about where that comes from, but for us that would be 4.5 volts. So the moment let's go back to our voltage at the capacitor plates, the moment that it exceeds 1/3 VCC, the output at pin 3, we'll call that output, of the 555 chip ends up going high. All right, like such. So the output of pin 3 is high, the capacitor is continuing to charge, and then eventually the capacitor's voltage will reach 2/3 VCC. And because the capacitor's plate is also tied to comparator 1, whose reference voltage is 2/3 VCC, comparator 1 will say, oh, hey, my positive terminal is now higher than my reference terminal, so I'm going to set my output for comparator 1 is going to go from low to high, okay? So if this goes high, that will then reset the flip-flop. And if the comparator 1 goes high, that will cause Q bar to go high, which will send our output to low, which in this case is about 0 volts or 0.1 volts. So as soon as this voltage hits 2/3, then the output drops down to about 0. Okay, now, here's the neat part. The neat part is that when Q bar goes high in response to the flip-flop being reset, you'll notice that the output of Q bar is also tied to this little guy, which is called a transistor. This transistor is functioning essentially as what we call a voltage-controlled switch. Now, when the transistor is turned on by Q bar going high, that essentially opens a circuit. And when I say opened a circuit, what I mean is it creates a short circuit. So that will end up connecting. If you follow this pathway, where does it go? Well, it goes, it's not connected here, it's not connected there. It's actually going to capacitor. So that will end up providing what we call the discharging path through R2 and all the way through the discharge transistor switch to ground. Okay? So what that's going to do is that's going to end up dropping the capacitor voltage, but with a different time constant. While the capacitor charged through R1 and R2, it's discharging only through R2. Okay, so it starts to drop, and then as soon as it goes below 1/3 VCC, comparator 2 notices. Comparator 2 says, hey, wait a second, the voltage at my negative terminal just went below 1/3 VC, that's my comparison threshold voltage, I'm going to set the flip-flop. So when it sets the flip-flop, comparator 2's output jumps back to high. That sets Q bar to low. That turns off the discharge transistor. And guess what happens? The capacitor starts to charge again. Okay, that also, the output there then goes high. So the output jumps back up to high, and the capacitor starts to charge again. Until when? Until it hits 2/3. 2/3 resets the flip-flop, turns on the discharge, starts to decay. Decays through 1/3. Comparator 2 sets the flip-flop, turns off the transistor, starts to charge. Reaches 2/3, and so on and so forth. Whoops, I guess I should have done this. Okay.